When considering applications of simple differential equations of higher order but still linear, one idea that might come to mind is something similar to the spring mass system, and that would be a pendulum that swings back and forth. Again, the physics is quite straightforward. There's only two forces applied here. We have gravity and we have the force of the rod or the cable that's holding up the pendulum mass, and a bit of geometry to get the angle of the force that is tangential to the motion. There are a few ways to go about looking at the physics of this. One of the most common ways is to go to circular motion physics, which is analogous to the F equals ma, only it's the sum of the torques rather than the sum of the forces that applies. We're not going to go through the massive derivation here, because not everyone will have taken physics, but at the end of the day, what we end up with is a second derivative for the angular acceleration, and we have something equivalent to the force here, only there's a coefficient for the length of the bob here that turns that into a torque. When we rearrange that a little bit, we can cancel some terms. The masses disappear, and 1L here disappears. And what we end up with is theta double prime, bring this over, we'll have plus G over L, if we divide through by that, sine of theta equals 0. This is a second order differential equation. However, it is nonlinear. The presence of the sine of the theta, and remember in this case here we'd be looking for theta equals, that makes it nonlinear. So why are we discussing it in a chapter on linear differential equations? Well, with this differential equation, we can approximate. And one of the approximations that you cover in calculus, and this would be a linear approximation, or if you like, and go back to your tangent plane, tangent line equations, the sine of theta can be approximated by theta itself. What do you mean? If that's not fresh in your mind, think of the sine graph, and if you look in detail right at the origin there, and you draw a tangent line, that line, if this was theta and sine of theta, that line there would be the straight line graph, zero intercept, and slope of 1. With that in mind, we can say our differential equation, the rule that applies, is almost exactly theta there instead of sine of theta, and presto, all of a sudden we have a linear differential equation. In fact, it looks an awful lot like the spring mass system, which is what we'd expect from a pendulum which swings back and forth, just like a mass would oscillate back and forth. However, there's a little caveat here. This is approximate, and the condition on this approximation is that the theta has to be near 0. And again, near is a qualitative argument, or small swings of the pendulum. And generally speaking, a rule of thumb would be under 10 degrees, which is still a pretty reasonable swing, certainly visible to the naked eye. If you're in that range, this is going to be quite a good approximation, down to 0.01 type of thing. So what we've done is studied a system, which is the pendulum, arrived at the differential equation from physics, and then if we want to predict the motion, we realized, well, our tools don't work on this because of the sine, but the sine of theta is approximately theta for theta being close to 0. And at least in that regime, we can approximate the solution with the solution to this linearized version. And so often this would be called the linearized differential equation. It's a very common technique when studying differential equations, because a lot of them end up being nonlinear, but we do this kind of trick to turn it into something that we can actually solve, even if it's only an approximation of the original. Once we've done that linearization, the solution problem is quite straightforward. We do our usual assumption, we get our characteristic equation, and that gives us r squared is minus g over L. So r is plus or minus the square root of minus g over L, which we will write as g over L times the root of minus 1. We'll slide a 0 in here. That becomes our A, that becomes our B, and lo and behold, we get that our angular displacement is going to be e to the at, that's just 1. So we're going to get a simple cos of root g over L times time plus another constant times the sine of root g over L times time. And that, of course, is a simple oscillatory solutions. Again, we can take advantage of this solution form and we can predict something we couldn't do before. If we just gave you a pendulum and said, how long does it take to swing back and forth? What's the period there? Well, we couldn't do that from the differential equation. There's not enough information, but the solution tells us that just by a simple interpretation of what cosine of bt does. The period will be equal to 2 pi divided by the coefficient of time, square root of g over L, and that will be square root of L over g times 2 pi seconds, assuming the units here are meters and meters per second squared. And what that tells us is a few key features right off the bat. That longer pendulums, which is a bigger L, longer pendulums have longer periods. And not too surprisingly here, we don't usually get to control gravity, but if g increases, so if we did this on Jupiter, then we would have a shorter period, faster oscillations. Usually L is the one that we have more control over in practice. Now again, all of our work there was done based on the assumption that theta was approximately 0 or near 0. So for larger angles, it should be maybe, again, we're going to be guessing here, similar qualitative, so not exact predictive quantitative values, similar qualitative behavior. Not a huge shock. What we basically mean there is that we expect to see oscillations. But it could be the swings, the motion could be much more complex. If theta is large. Now, does that seem reasonable to say? I mean, we look at pendulums and think they're pretty simple, and that's fine. But imagine, if you will, if we had a pendulum that swung out to here, and then we pushed it, well, it might actually go almost to the top, slow down, and then come back, or it might go over the top, and we might actually have a pendulum that goes in circles forever if there's no friction. Those are very different kinds of behavior that do not match at all this simple cos plus sine, back and forth, back and forth. And that's where the breakdown happens. If we choose angles that are larger or far away from 0, we can get all sorts of other interesting things happening, but they're not the kinds of thing that that simple linearized model could predict. So that's what we lose with that linearization, that simplification.